Welcome back to Digital Systems 1. In this video, we are going to discuss arithmetic digital circuits, which means we're basically going to take the concepts we've learned from binary addition and design a circuit that can perform that addition for us. We'll also look at circuits that currently exist, including the 74HC283, which is an adder IC. So now that we know how to add binary numbers by hand, let's discuss how we would design a circuit that can complete that addition for us. So we're going to use an example just to kind of cover this idea. So if we need two numbers that we're going to add together, let's say we're going to add the number 10101 and the number 00111. Well, we're going to need some way to perform the same process that we used to add together binary numbers by hand, which means we need some process to add the 1 and the 1 together, to come up with the 0 and the carry, and then to carry that particular carry bit forward to the next set of addition that we're going to do. So we're going to use the concept of something called a full adder to implement this idea. And on the right is a block diagram of the full adder, FA for short. When we think about what the full adder has to do, we want the full adder to take an input A, input B, and add them together, and then give us a sum, and then give us a carry. We also need the full adder to reflect what if I had a carry coming in from somewhere else that I would also need to consider. For example, if I'm going to add 0 plus 1 in this second column here, I also have to consider the carry from the last operation that was carried forward. So I'm really adding 1 plus 0 plus 1. So we need a circuit that will be able to take an input A, input B, and possibly the carry coming in, and determine what's my sum and what's the carry going out that would go forward to the next set of addition that we're going to perform. So when we talk about the idea of a full adder, we're talking about a circuit that can implement just one piece of this process. We're talking about a circuit that can basically just perform one step at a time. So maybe just this step in the yellow box, or maybe just this step in the second yellow box. We need a circuit that will take input A, input B, a carry going in, and determine my sum and what my carry going out would be. Then I could take a bunch of these and string them together to add up a very large number. So what we're going to do is design what would be going on inside of this box. What would be going on inside of the full adder in order to produce those results. So once we get those results, the idea is that we could take one full adder and string them together to create a series of full adders that could add up a number. Say this number B4, B3, B2, B1, B0. That's input B, which has 5 bits. So if I have an input that has 5 bits, I need 1, 2, 3, 4, 5 adders so that I can add up each of those bits to another input. See, this is our second input down here. So what we want is a full adder circuit that can basically take input A0, input B0, possible carry coming in, and determine the carry going out plus a sum. If we string these together, all of a sudden we have a circuit that can perform addition. And all we need is one full adder for each bit in your number. So a 10-bit number would need 10 of these, a 100-bit number would need 100 of these, etc. But it's a circuit that would add up your two inputs plus your carry coming in and determine your sum and your carry going out. So we're going to design that. So just like we talked about earlier in the semester with the design process, we always have to start a design with a truth table. And so on the right, you'll see our diagram for the full adder. You'll see that it has 3 inputs, input A, input B, and input C in. That stands for carry in. So we have our 3 inputs labeled on our truth table. Notice the inputs are set up just like any other truth table. Now what we're going to do is we're going to determine what is sum supposed to be and what is C out, that's the carry going out, supposed to be if the inputs are listed as shown here. So for example, if the input is 0, 0, 0, That means I'm doing 0 plus 0 plus a carry of 0. That would give me a sum of 0 and a carry out of 0. And I'd write that down. Next, I'd be doing 0 plus 0 plus 1. That would give me a sum of 1 with no carry. And I would write that down. So as we fill in the truth table, that's literally what we're going to see. 0 plus 0 plus 0 is a sum of 1 with no carry. 0 plus 1 plus 0 is a sum of 1 with no carry. 0 plus 1 plus 1. Here's an important one. Remember, we're going to apply the same idea we did when we added two numbers by hand. 0 plus 1 plus 1 is going to give you 0, carry the 1, the same way you write it by hand. That's how it's going to go in the truth table. And then we're going to continue that. 1 plus 0 plus 0 would be 1 with no carry. 1 plus 0 plus 1. That's like saying 1 plus 1. That's going to be 2. 0, carry the 1. Same thing here. We have 1 plus 1 plus 0, which is again 0, carry the 1. And then we have 1 plus 1 plus 1. When we did that by hand, 1 plus 1 plus 1 was 1, carry the 1, and that's what you'll see in the table. So your sum is like what you'd be writing down at the bottom of your number when you're adding two numbers together, and the carry is exactly the same carry you would write down when you're adding two numbers together. Now that we have a truth table that describes how the circuit should work, the next step in the process is to make a K-map. Here's the K-map for sum. If you were to take that truth table, make a K-map for sum, which is the S. Make a K-map for sum. This is what your K-map would look like. Notice that you can't make a group of 2 anywhere. So if you were to write out the equation for the output for sum, here's what it would look like. We have 4 ones, none of them will make a pair, so you're going to write out the term, the SOP term for each one of those ones. And here's a case where you're going to have to do a little bit of Boolean algebra to simplify this, because a K-map can identify examples where there might be exclusive or exclusive NOR. And this is a case where you're going to need one of those. I'll show you how. So I'm going to take this expression and we're going to simplify it. So here's the expression. The first thing that we're going to do, see what common terms we can factor out. You can factor not A out of the first 2 terms, and you can factor A out of the second 2 terms. Now, if you look at this term right here, remember, exclusive OR is when you have one high and one low, or the other one high and the other one low. That's exclusive OR, which is right here. And then exclusive NOR is when they're either both high or both low. So this becomes exclusive NOR right there. Next, we're going to let this piece be called X, which means this piece would be not X. So if I can substitute all of this, the B exclusive OR CN, with an X, then the B exclusive NOR CN would be the inverse of that, not X. And what we have here is another expression for exclusive OR. If we have not A and X, or A and not X, that's saying A is exclusive ORed with X. Now we're going to substitute back in what X stands for. We said that X would stand for B exclusive OR C. So when we have A exclusive OR X, what we really have is A exclusive OR B exclusive OR C. So the expression you get from your K-map is not going to be as simple as it could be, because K-maps will not help you to really identify areas where their exclusive OR and exclusive NOR apply. So we had to use some Boolean algebra to simplify this. So the output for your sum is that A is exclusive ORed with B, which is exclusive ORed with CN. That is the equation we're going to be using to develop the circuit we need implement the sum coming out right here. So that's the equation for sum. Now let's do the equation for C out. Here's the K-map for C out. Again, you're going right based off of the truth table that we created. Here's C out. Make a K-map for that output. And here's what that K-map would look like, with 3 circles, each with a group of 2. When you write the SOP terms for those circles, you get B and C in, or A and C in, or A and B. So I have 2 equations that I now have to draw a circuit for. One for C out and one for sum, which has been simplified to this over here. So if I can draw a circuit to implement those 2 equations, I have a circuit that will add 2 pieces of information together. It will add input A plus input B plus your carry in and give you a carry out. Here's what that circuit would look like. Remember, sum was A exclusive OR B exclusive OR C. Here's the exclusive OR for B and C, C in, and then that gets exclusive OR with A. So there's your sum. Then your C out, you have 3 AND gates and an OR gate to implement this expression right here. So this is my circuit that's going to become the full adder. This circuit will take input A, input B, and your carry in, give you a sum and your carry out. Now we have a circuit that'll do some of the work for us. So imagine this diagram right here. We designed the circuit inside one full adder, just one. Now imagine that we chain a bunch of those same circuits together. We can extend that idea from adding just 1 bit to another bit to now adding 5 bits to another set of 5 bits. And now you have a full adder circuit that can add 2 inputs together for you. So let's take a minute to sort of analyze how this would work, remembering that what's inside of each of these full adders is the circuit right here. So this circuit is now being replicated 5 times, where the output of 1, the carry from 1, becomes the input carry to the next. And we're going to analyze how this works. So we have 2 questions we're going to answer. How many inputs does this parallel adder have, and how many outputs does it have? And then we're going to assume the following input levels. You're given an input for A, an input for B, and an input for your carry 0. And we're going to figure out what are the outputs for the second full adder as well as the last carry output. So let's start with inputs and outputs. If we go back to the picture here, an input is anything going into the adder. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 inputs plus this input right here. Those are the things going in. So you have 11 inputs. And then what's coming out of the adder? And by out, I mean what's coming out as an output the user could see. Something that might be like connected to an LED. That would be your sum. That's 1, 2, 3, 4, 5. Plus your final carry. 6 outputs. So we have 11 inputs, 6 outputs based off of what goes into the adder circuit and what comes out as an output. Notice these carries are carried forward as an input to the next one, so they're not really considered an output that we would see as like an LED. Next, we're going to assume that input A and input B have a certain value. So input B is 0, 0, 1, 1, 1. Input A was given as 0, 1, 0, 0, 1. And I've simply replaced each label on the picture with the value you were given. So it told you that B4, B3, B2, B1, B0 had a certain value, 0, 0, 1, 1, 1. So I just filled those values in. I filled the values for A in at the bottom, and I filled in the value for the carry, C0 right here. Now we're going to look at what this adder will do. The first full adder will go 1 plus 1 plus 0. It will take those three inputs, add them together. 1 plus 1 plus 0 is 0, carry the 1. So S0 will be a 0, C1 will be a 1. Now this next full adder will go 1 plus 0 plus the carry coming in, and it'll add those three things together. 1 plus 0 plus 1 is 0, carry the 1. So the sum here will be 0, and another carry of 1 comes out here. The next full adder will do the same thing, and we'll go 1 plus 0 plus 1. And you'll get again 0, carry the 1. The next full adder will do 0 plus 1 plus 1. Remember, that's now an input. 0 plus 1 is again 0, carry the 1. The last full adder will do 0 plus 0 plus 1 for a sum of 1 and a final carry of 0. So now we can see that the output of each full adder is shown in blue, and the sum is here at the bottom. So when we add the number 00111 to the number 01001, the final answer is 10000. And ask yourself, does that make sense? 0111, that's 7. 01001 is 9. 7 plus 9 is 16. And this answer, 10000, is 16. So it is adding that up correctly. We can also see that the output for the full adder number 2, the outputs for full adder number 2, you're going to have a sum of 0 and a carry of 1. And then the output of C5 is a 0. So this is an implementation of that circuit that we just designed. You can take the circuit from the previous page, you can build that on a breadboard, you can then duplicate it and connect them together, and you will have a circuit that can perform addition for you. So there were the answers showing the logic levels for flip-flop number, I'm sorry, not flip-flop, for the full adder number 2, as well as the logic level at the C5 output, as we just discussed. Now, that was the implementation of what we call a full adder, and sometimes, in some cases, you have a circuit that you'll need that will only add 2 inputs to produce a sum and a carry, and you don't have that third carry input. This is called a half adder. That's a special logic circuit that we're going to design to take 2 inputs, A and B, and produce just a sum and a carry. You only have 2 inputs instead of 3. It's called a half adder. So let's talk about how we would design the half adder. If you only have 2 inputs, you've only got A and B, that means your truth table is only going to have 4 rows. And then we're going to determine the sum and the carry just for those 4 rows. So if you have A plus B, that's 0 plus 0. Your sum is going to be 0. Your carry will be 0. 0 plus 1 gives you a sum of 1, carry nothing. 1 plus 0 gives you a sum of 1 with no carry. 1 plus 1 gives you a sum 0, carry the 1. Now we have a really simple truth table that we don't even really need a K-map for, because we can see that sum is only high in these 2 rows. You have not A and B, or A and not B, which is A exclusive OR B. And then we can see that carry is only high when A and B are both high. So now we have 2 equations for the half adder that are a lot simpler than the full adder because we have less inputs. Now, we've discussed how to design an adder, but there are also ICs, or chips, that you can use that are already set up and designed to perform addition for you. So instead of you getting some AND gates and some XOR gates and trying to build an adder, you can buy an IC off the shelf that will add 2 numbers together for you. That's what the 74HC283 does. This particular part number is a 4-bit parallel adder. So it's a chip that you can just place onto your breadboard. You can give it any inputs you want for input A, any inputs you want for input B. Notice those are each 4-bit inputs. You provide it with a carry in. It will add your 2 inputs plus your carry in, give you a sum and a carry out. So it basically will do the addition for you. And you could think of connecting inputs A and B to like switches, and you could set the switches high or low depending on what number you wanted to add together. And the 4-bit parallel adder is basically an implementation of that idea that we discussed. So if you go back a few pages in the notes where we drew the actual circuit for the full adder, the parallel adder just takes that concept and puts it on an IC for you. It's all packaged and ready to go. The nice thing about these particular ICs is that they can be cascaded. The picture on the right shows the idea of cascading 2 chips together. And that just means that the output of one chip becomes the input of another. So in this example, we have 2 74HC283s, where the first one on the right is going to add up half of the number. It's going to come up with a carry. Provide that carry to the second half of the number, where the second chip is going to add the second half of the number plus the carry to give you a sum and a final carry out if there is one. So cascading is something that's very common because the 4-bit parallel adder is only great for 4 bits. What if I need to add an 8-bit number together? What if I need to add 2 16-bit numbers together or 2 12-bit numbers together? I would have to cascade the 4-bit adder in order to do that. So this is what cascading looks like, and you would have your higher order adder. Basically, this adds up the first 4 bits, the more significant bits, and this side adds up the smaller, the least significant bits of your number, the lower 4 bits. And your output here is going to be an 8-bit number, which represents the sum of those numbers with a possible carry coming out right here. So now let's take a look at how this would work. So we're going to determine the logic levels at the inputs and outputs of the 8-bit adder in this figure below, figure 611, when 72 base 10 is added to 137 base 10. So now we have a 4-bit parallel adder that's been cascaded. Then we have to determine what the inputs and outputs are going to be in order to add these 2 numbers together. First thing you're going to need to do is convert each number into binary. So 137 would come out to be 10001001. The number 72 would come out to be 01001000. Now you can call this input A or B. It doesn't matter. One of these is input A, the other is input B. So we're going to consider 137 to be input A. We're going to consider 72 to be input B. So the lower order adder, the one on the right, is only going to add up the bottom half or the lower order half of the number, which means it's only going to add the 1001 and the 1000. It's going to add that up. 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0, carry the 1. So right here, this carry would be a 1, it would be high, because the lower order would determine that when you add up the lower 4 bits, you end up with the carry coming out of 1. This adder is going to combine the 1000 with the 0100 and the carry coming out of the lower order adder. It will combine all of those values to get 1001 for its sum, and then you combine the sum together for a final answer. When you combine input A and input B together, your final carry will be a 0. So C8, the C8 bit, will be 0. You don't have a final carry out. If you did have a final carry out, there would be overflow because your answer is technically 9 bits long with the carry, but your sum only has space for 8 bits. So you would be watching out for a case where you might have overflow. If that C8 bit is high, you have an overflow issue that you would need to address. And this is the end of the video for arithmetic digital circuits.